Ask me during the tea time.
Tea time. Thank you very much. So we go to the next talk by Ramesh Kaul on topological parameters in quantum gravity, in gravity, topological parameters in gravity theory. Ramesh Kaul does not need any introduction. He has already addressed you here. And I just wanted to make a remark. He is actually originally, at least in the earlier incarnation, at least he was a particle physicist, high energy physicist. Now high energy physics now includes gravity, as is clear from his shift and the shift of many other people. Ramesh Kaul.
So I'll talk about topological parameters in theory of gravity. The outline of my presentation is that I'll discuss briefly topological density terms, total derivative, which are total derivatives in the Lagrangian density of a quantum mechanical model, as well as in QCD. And then I'll make a case that there are three such terms in a theory of quantum gravity in 1+3 dimension. These three terms are given names: neon, Pointryagin, and Euler densities. And associated with these three terms, there are two CP odd and one CP even parameters, and one CP odd parameter, which is identified with the coefficient of the neon term, is really the inverse of what is known as Barbero-Imizzi parameter. I'll set up a classical canonical Hamiltonian formulation for the theory of gravity, including all these three topological terms. And in the time gauge, we'll see that we obtain a real SU2 gauge theoretical formulation with a set of 7 first-class constraints, 3 corresponding to SU2 generators, 3 to diffeomorphism constraints, and 1 Hamiltonian constraint. And in this process, this whole analysis will provide us a topological interpretation of what is known as Barbero-Imizzi parameter. So let me start with introduction. Fact in classical mechanics that Euler-Lagrangian equations of the Lagrangian formulation do not change by so if I have some classical mechanics system described by Lagrangian density L0 and this does not change the equations of adding total divergences in the Lagrangian density in the Hamiltonian formulation only implies a canonical transformation of the coordinates, old coordinates q, u prime as a function of old coordinates and momenta, and old momenta changing to new momenta as a function of old coordinates. And a corresponding change in the Hamiltonian to a new Hamiltonian h prime, which is a function of the new coordinates and momenta. Thus, the equations of motions don't change, the phase space changes, so does the symplectic structure. Yet the Hamiltonian equations of motion are the same, and the equations of motion are identical with the Euler-Lagrangian equations of the Lagrangian formulation. So I repeat, classical dynamics, that means classical equations of motion, do not change the divergence terms in such a total divergence. Generally speaking, even quantum theory does not see total divergence terms. Total divergences of the type what are called topological have a special such dynamics is not affected. So the physical constant will develop dependence on the coefficient theta divergence term. And this happens so is that canonical transformations of the classical Hamiltonian theory in a quantum theory are implemented through unitary operators on the states and the phase space operators. Such a unitary implementation of canonical transformation in a quantum theory does not obtain always. there can be some topological, in some situations, obstructions to implementing such an implementing unitarily the canonical transformations in the quantum theory. So thus, for a quantum theory to have dependence on parameter theta, which is the coefficient of the total divergence, it should be a coefficient of a topological density. This is a necessary requirement, but not sufficient. Parameter theta. And this constants of like electromagnetism and gravitation, except that
this is off. Okay.
Is that all right now? Of course, coupling constant and electromagnetism Newton constant exist both in classical and quantum theory, but such topological operators are coupling constants only in the quantum theory, because in classical theory they are irrelevant. Another interesting properties of such topological densities are that they are universal, in the sense that they don't depend upon what additional matter you may add to such theories, any additional matter couplings you may have in such theories. So let me give you a simple example of such topological densities. A total derivative dx by dt with a coefficient theta normalized for convenience by a factor of 1 by 2 pi. The equations of motion for this system is second derivative of x with time plus a variation in potential with respect to x is 0. There is no dependence, no sign of the total divergence term. There is no dependence on parameter theta. So the presence of total derivative term does not affect this equation of motion. There is no theta dependence. Now this total derivative term that I have written here is indeed a topological density, and in fact its integral is a topological charge or the winding number for periodic configurations xt, and the charge is measured by this integral from minus infinity dx dt dx dt with normalization 1 by 2 pi. And this charge just measures how many times do we wrap or wind xt over the interval 0 to 2 pi as we go around t once over its full range. So for example, x equal to plus minus 4 tan inverse exponential t minus t0. The topological charge is treated with such a configuration is just simply this integral, its values plus 1 and minus 1. So the integer in fact is plus 1 and minus 1 for this set of configurations. It's always an integer. And it's always an integer because the basic fundamental fact, that is the total derivative term that we had introduced in this theory, is indeed a topological density associated with homotopy maps of S1 to S1. And these maps are characterized by the homotopy group of S1, which is a set of integers. So now let's go to this potential that we introduced for this mechanical model, the periodic sine Gordon potential. Vx is the coupling constant lambda 1 minus cosine of mx root lambda. In this case, the quantum theory does indeed depend upon the topological parameter theta that we introduced. This potential has infinitely many classical ground states given by the location when this argument here mx ground state values are 2 pi n root lambda for integer n's. And corresponding to each one of these classical ground states, there is a perturbative vacuum state represented by an integer label n, ket n. If we were to ignore tunneling between these various vacua, then the quantum states would be an infinitely many degenerate states, each concentrated at the bottom of these veils. But quantum barrier penetration will lead that every energy eigenvalue to be changed into a continuous band of eigenvalues, the so-called block wave. This is so because the real quantum vacuum state here is a non-perturbative one given by the linear combination of the perturbative quantum states n. So the real vacuum state is a linear combination of these perturbative vacuum states with the weight exponential I and theta. And this is exactly the one, the coefficient of the total divergence term properly normalized there earlier. So in this theory, what associated with the quantum vacuum states are infinitely many classical ground states, corresponding to infinitely many degenerate minima of the classical potential. But the vacuum state is essentially non-perturbative. But the quantum vacuum state non-perturbative in character. And physical quantities do depend on the parameter theta. For example, if we were to study the ground state energy for the system, besides the perturbative 0 point energy half h cross omega, there is an non-perturbative contribution theta. So the true vacuum energy for this is the 0 point energy plus E theta, where h cross lambda. Lambda is the coupling constant of the theory, B is some numerical constant. So there is a dependence on this parameter cosine theta here. And example of theta. And earlier, but what it means is theta is an additional coupling of the quantum theory. Like the electromagnetic coupling constant is not determined by the theory. So mechanical example is actually an example of a topological density term in the Lagrangian density. The QCD Lagrangian has the standard QCD Lagrangian term minus 1 by 4 g square of the field strengths minus theta times H3 gauge field strengths. Yeah, is indeed a topological term. Oh. Should I put it here? So this term that we have added to the Lagrangian density theta times 64 pi square epsilon times square of F's, is indeed a topological density, and it's known as the Pointryagin density. It's a total divergence. I have explicitly written down here that half epsilon mu alpha beta F mu F alpha beta is 4 times divergence of a vector Kp, where K is epsilon mu alpha beta, A nu del A beta, 1/3 Fi jk's are SU2 structure, SU3A structure constants times 3A's. This is the well-known Chern-Simons form. And in the Euclidean space-time, integral of this density, properly normalized by 64 pi square d4x epsilon times 2f's, is indeed an integer. And it's so because this topological density that we have here measures the winding number of homotopy maps of S3 to S3 characterized by the third homotopy group of SUN. The n is 3 for a QCD, which is set of integers. So like the mechanical system with periodic Sine-Gordon potential, there are infinitely many classical ground states in this theory also. And each classical state, classical ground state, is characterized by the integer n. And these are given by the solutions of the equation that the field strength is 0, which are just pure gauge. A mu Ti is G inverse G d mu G, where Ti are SU2 algebra representation matrices, and G is an element of the gauge group SU3. These elements Gx fall in homotopy equivalence classes, each characterized by an integer. And the true non-perturbative quantum vacuum state in this theory is also again a linear superposition of the perturbative vacuum states associated with these classical ground states. So true quantum vacuum is exponential I n theta n. And this theta is the same theta that we introduced as the coefficient of the total divergence term. Notice this is the total divergence term we had introduced, epsilon times 2f's. And because of presence of this epsilon, this is really a CP violating term. So the QCD in fact is a theory of two coupling constant, the standard gauge coupling constant and a CP violating coupling constant theta. And physical quantities do depend on this parameter. For example, in quantum theory, there is a non-zero electric dipole moment for the neutron which depends on theta. Thus, theta is a physical parameter which is to be fixed by experimental constraints on possible induced CP violating effects. These constraints force this parameter to be extremely small. In fact, the constraints from the electric dipole moment of neutrons suggest theta should be less than 10 to the minus 10 radians. Now, with these two examples of situations where total divergence terms in the Lagrangian density are quantum mechanically relevant, let me go over to the case of gravity. So let's explore the possibilities of such topological coupling constants in a theory of gravity in 1 plus 3 dimensions. In gravity, we set up a theory of pure gravity, no matter couplings, in terms of 24 SO1, 3 gauge connections, the omega ij's, and 16 tetrad fields as the independent fields. Described by Hilbert-Palatini action, 1/2 E sigma mu nu ij, r mu nu ij, where E is a determinant of the tetrad, and sigma mu ij r is the antisymmetrized product of the inverse tetrads, and R is the field strengths of SO3 1, 3 gauge theory. To this Lagrangian density, there are three possible topological densities that we can add in 3 plus 1 dimensions. The first one is called the neon topological density. Its form is E times sigma mu ij. Sigma mu ij is where the antisymmetry, it's a product of inverse tetrads, times r mu ij. Dual is in the internal space ij, plus epsilon times covariant derivative of tetrad, completely antisymmetrized in all the indices mu, nu, alpha, beta. This is indeed a total divergence as the topological density should be, and I have explicitly written it down here. It's d mu of epsilon times tetrad times covariant derivative of tetrad antisymmetrized in the indices. While the dual here is explicitly given here, is the dual in the internal SO3, 1 space. This neon density is a total divergence, which is what it makes it, whichever topological density has to be. But it's indeed a topological density because it does measure the topological properties. And this is the covariant derivative here is covariant derivative only with respect to the SO3, 1 group. So this is a topological density and is a total divergence. In the Euclidean theory, this topological density, properly normalized, characterizes the winding number given by 3 integers associated with homotopy groups of the third homotopy group of SO5, and the third homotopy of group SO5, which is given by one set of integers, and the third homotopy group of SO4, which is given by set of 2 integers. And notice there's one dual here, so there's one epsilon here, and also there's one epsilon in this term. Like the theta term of the QCD, this is a CP odd density. The second topological density that we can add in 3 plus 1 dimensional gravity is the Pointryagin density. Epsilon mu alpha beta is r mu nu ij, r alpha ij. And this is also a total divergence, which is what I have explicitly displayed here, is the divergence of this object, gravitational Chern-Simons. This is the same topological density as in the case of QCD, except the fact that gauge group here is SO3, 1 rather than SU3. And for the Euclidean theory, this topological density, properly normalized, characterizes the winding number given by 2 integers corresponding to the homotopy group, the third homotopy group of SO4, which is given by 2 sets of integers. So this is again this topological density, because there is one epsilon symbol sitting here, is CP odd. Third density that can be added to the Lagrangian density of gravity is the Euler class. This is epsilon times r mu ij, r dual r. This is the same expression except that one of the r's is dualized in the internal space. And like any other topological density, it's a total divergence, which I have displayed here. Omega dual is the dual in this ij space, internal SO3, 1 space. Now, unlike earlier 2 topological densities, notice there are 2 epsilons here. One is epsilon here and one is in the dual. So it's not a CP odd, but a CP even topological density. So the most general Lagrangian density that we could have in gravity is the Hilbert-Palatini action. To that you add the neon and Pointryagin and Euler with coefficients eta, theta, and phi, and some convenient normalization factors. And like we said earlier, since all topological density terms, all these are total divergences, this classical equations of motion are not changed by including them. So which means that equations of motion are independent of these coefficients eta, theta, and phi. However, Hamiltonian formulation and the symplectic structure do see these parameters. So the quantum theory may depend on them. And like we said earlier, that the neon density and the Pointarian density are CP violating, whereas the Euler density is not. So what we have is that these coefficients of these terms, eta, theta would be CP odd, and phi is CP even. So what we have is a quantum theory of gravity which, besides a Newton's coupling constant, has two additional CP violating, eta and theta, and one CP preserving coupling constant. So now let me try to set up the Hamiltonian formulation for this theory. Now Hamiltonian analysis for the theory containing the Hilbert-Palatini term and the neon term only, which means eta non-zero and theta and phi 0, was done some time back, which means for a theory which contained the Hilbert-Palatini plus neon. And what this analysis led to was that this analysis in the time gauge leads to the well-known Asteker-Barber-Ramirez real SU2 gauge theory of gravity with eta, the coefficient of the neon term, eta inverse, identified as the Barber-Ramirez parameter. In the time that I have now, I'll present a brief outline of Hamiltonian analysis of Lagrangian density containing all the three terms, means with theta and phi non-zero in addition to eta non-zero, which means the Hamiltonian analysis for the Lagrangian density of Hilbert-Palatini plus neon plus Pointarian and Euler density. We start with the standard parameterization of the tetrad fields, that ETI is the lapse times a time-like internal vector mi times shift vector times VIA, where VIA is the same as the tetrad space components. And the inverse tetrads are given by these relations. In this parameterization, we have, instead of 16 tetrad components, we have the following 16 fields. 9 VAIs, A runs over space labels, I is the internal space with the constraint that with a time-like internal space vector this is 0, so there are really 9 independent variables here. There are 3 independent variables in the MI vector and 4 variables here, 1 lapse and 3 shift vectors. From these we define a more convenient set of tetrad variables, where EAI is twice E sigma T0I. Sigma T0I is the anti-symmetrized products of the tetrads, and chi is the space component of the M vector, and the shift and lapse and the shift variables. So there are 9 of these, 3 of the chi's, 1 n, 1 n, so again 16. And of the 24 connection variables omega ij, we set up a convenient set, which is A, omega eta 0, omega 0 I plus eta times omega 0 I dual. Dual is in the space, internal space omega I. And the ki, which is omega 0 I, and omega t ij, these are 9, these are 9, and these are 6, 24 of them. In the time gauge, we set up chi equal to 0, and so some of the tetrad components are 0. And in this gauge, the Lagrangian density that we started with has a very simple form. It's a some E hat derivative of this A, F hat derivative of this K, and T hat derivative of V minus H and some total derivatives, where the pairs A and E hat, K and F hat, and V and T hat are canonical conjugate pairs. And E hat is given in terms of the old variable, which is in fact which is in the time gauge is nothing but a densitized triad density, plus 1 plus eta square F hat plus some function of A and K which depends on theta and phi. And F hat is this object. And this E variables are explicitly displayed here. They depend on theta and phi and eta through these combinations. And theta was the coefficient of the Pointryagin density, phi was for the Euler density, and eta of the neon density. The fields VAI, TI, and FI are not independent fields. In fact, they are specific functions of the other fields. VI is given in terms of EI like these. TIs are given in terms of other fields like this, while EA down is inverse of the EA up, and E is a determinant of E. And the Hamiltonian density here in the time gauge has the form that it's the lapse times an expression H, which is Hamiltonian to be identified with Hamiltonian constraint, Na times Ha, omega Tij g to rotation, and expressions which reflect that V, T, and F are not independent fields. There are some specific expressions Va, tau I, and E hat of other fields. Explicitly, G rotation, because it's been given a name rotation because the generator of rotation is eta times is covariant derivative of A, covariant with respect to the SU2 gauge field A, and epsilon ij k hat, k times f hat, T and V. HA in this expression is this combination. And H is this combination, where in H, EA is given in terms of E hat and F hat, and in terms of these objects. Now these fields N, Na, and omega Tij, these have no derivatives in the Lagrangian density. Therefore, they are Lagrangian multiply fields. So corresponding to them, there are as many constraints in this theory. So the constraints are that this G rotation, Ha and H are 0. In addition to these, we have also the constraints due to the fact that Va and Ta and F hat are not independent fields, which are given by that Va is some specific function of E's, and Ta is a specific function of these, and Fa is a specific function of these, and I write chi A equal to Fa hat minus 2 eta plus 1 plus eta E hat equal to 0. This is a constraint which tells us that F is not an independent, F hat is not an independent field. The constraints chi ai are of a particular interest. Since A and E hat and K and F hat are canonically conjugate pairs, these accordingly obey the standard Poisson-Braket relations. Using these, we obtain a secondary constraint by taking the Poisson-Braket of the Hamiltonian constraint with this constraint chi A. And that second class constraint, secondary constraint is that TA is an expression of this kind in terms of the basic fields E's and K and A. This can be rewritten in a form, and recall that TA itself was not an independent field, but was given by a specific combination of this kind, which is the same as this. So what this secondary constraint is, that really TA is 0, is weakly 0. So thus we have the secondary constraint that this object is 0, which we can solve for extrinsic curvature Ka and recast the following secondary constraint, that psi A is Ka minus kappa A, where kappa A is a specific function of E's and A's. So this is an additional constraint in the theory. But it forms a second class pair with the constraint we had chi A. So the Poisson-Braket of chi A with psi A, chi AI, psi A JB at equal time is delta AB minus delta AB, delta IJ, 3 delta function of x and y. So to implement the second class constraints chi A and psi A, we need to go over from Poisson brackets to the corresponding Dirac brackets. Then impose the constraints strongly that chi A and psi A are 0. It's a straightforward calculation to check that the Dirac brackets for the fields A and E hat and extrinsic and its conjugate field F hat are different from their Poisson brackets. On the other hand, the fields A and E, Dirac brackets are the same as their Poisson brackets. So finally, after implementing all the second class constraints, the set of second class constraints, the set of first class constraints we are left with are the rotation constraint, eta times covariant derivative A of E hat is cross product of extrinsic curvature and its conjugate momenta. HA is E hat contracted with FIAB, F hat I covariant derivative A of extrinsic curvature antisymmetrized. And the Hamiltonian constraint is this form. Where now we have the following to hold strongly. The second class constraints hold strongly now, that K is equal to kappa, which is this combination, and F is equal to this object, where this object is the dual of this object, which is a function of A and K. The effect of gauge transformations on various fields can be obtained, has to be obtained through Dirac brackets. For example, if I were to calculate the Dirac bracket of the rotation G rotation over E hat, it transforms. It gives me an answer of this kind: epsilon I j k E hat delta of 3 of x y. Or G rotation of a Dirac bracket of the gauge field A gives me an answer of this kind: is eta times delta ij derivative with respect A 1 by eta I k j a k a delta function x y. Or for example, if I were to calculate the rotation Dirac bracket the rotation with the F hat, which is the conjugate of extrinsic curvature K, then it gives me this answer. And similarly for this and this. All these just reflects that GI rotation are just generators of SU2 transformations on these fields.
Something happens to under parity to the second equation. A has some behavior at parity, and the right hand side is mixed, right? One side and the other
Yeah, you see, this is yeah. I mean, you can get back to what you are saying is that by scaling by eta. In some sense, this A is parity odd here, as opposed to what should be the normal definition. Is that's the concern, right? Huh? Yeah, that's right. Yeah, that's if you want to make A to be parity even, what you have to do is that A has to be scaled by an eta, which is parity odd, and then these will have exactly the kinds of expressions. So what the Dirac brackets of, similarly for generators of diffeomorphisms, the Dirac brackets of HA with various fields yield the Lie derivatives of these fields modulo SU2 gauge transformations. So what we have done is, we have provided a Hamiltonian formulation of the theory of gravity with 3 topological terms in terms of an SU2 gauge theory. Now this analysis includes all the 3 topological terms as against one topological term, neon term, that was done earlier. The coupling constant of the gauge theory is 1 by eta. This is to be identified with the Barbizon-Mizzi parameter. Now if we couple matter such as the fermions or spin half or spin 3 half, which is say maybe a supergravity theory, or any other matters, antisymmetric gauge fields to this theory, we do that in the usual way by minimal coupling rules. And an Hamiltonian analysis in the time gauge can be set up for, again, for all such theories, and they will all result into a real SU2 gauge theory with eta, inverse eta as its coupling constant. Yeah, I think that's all I have to say.
Thank you, Ramesh. So, if there are questions, yes, Bob. Bob. Yeah.
Can you explain how SO5 got into the picture in pure gravity without spin? Because there is no, if you go to Dirac gamma matrices, I can imagine, but then I have some other comments.
See, the neon density that I wrote here, for, let me think of a Euclidean theory, because that's what SO5 is really. The neon density that you have here can be written as a difference of a SO5 topological point transient density minus an SO4 point transient density, where you construct an SO5 gauge fields as a combination of the connection fields of SO4 and the tetrads. Tetrads give you the additional SO5 gauge fields. So that's what. So therefore, the topological properties of neon reside in these two groups.
Then, well, maybe it is a little technical, but so far as I know, the there is a SO5 is it's not a Cartesian product of two S3s modulo torsion. It is something.
Yes.
Then I believe there is a general theorem that any map of S3 into such a space can be deformed into some chosen SU2 subgroup or SO3 subgroup.
Yes.
So there is only one bundle you can construct.
That's the reason there is one integer. SO5 has only one integer. That's what I said.
But you can always
only
work with
the
SO5
pi 3 of SO5 is just one set of integers.
Yes.
That's
Since
what.
you started from SO5 and SO4 is a subgroup of that, one can always work with SO5. Then
No. See, SO4 has two of them.
Yes.
Right.
That can
Whereas SO5 has one of them. Right. So the configuration that you have is a combination of these. So both of them would be relevant.
Any other question? Yeah, question.
This global properties of space-time you're talking about, does it have any implication about preventing singularities? Because if there is something that cannot be shrunk to zero,
now clearly what one has seen is that one is getting essentially, not essentially, exactly the canonical, classical canonical formulation of SU2 gauge theory of Ashtaker, Barbero, and Imizzi. That is the basis of this. So quantum theory based on that is exactly, has already been talked about in the earlier talk here, is this doesn't add anything new to that structure. It in fact, it just extends with respect to these two parameters that structure.
Can you go there?
So this treatment you did, I mean, adding of Lagrangian terms, can this be done for higher dimensions also? And if it can be done, I mean, do the number of terms that you can add increase?
Yes, it can be done in any dimensions. I did, for example, quantum mechanics problem first, and that was in 0 plus 1 dimensions. Okay. And then I did it can be done in higher dimensions also. In higher dimensional gravity, I mean, the three that I listed as the possible topological densities are in 3 plus 1 dimensional gravity. In higher dimensional, this number may be different. There may be other terms that you may need to.
Any other question? Yeah.
And do you know, if you want to get a non-trivial topological charge, I mean, if you integrate these configurations, at least for the ones which depend on the tetrad, is there any statement about whether the tetrad has to be degenerate somewhere, or do you know of any?
I don't know, but very likely yes.
Okay. Because the degeneracies of the Lagrangian formulation and the Hamiltonian formulation are completely different. And when you go to the Hamiltonian from the Lagrangian, you have to invert various things. And so it's a bit different from gauge theory. Just a small. That was just
no, that's the problem from gauge theories also. See, gauge theories also, gauge configurations become degenerate at places. So, yes, I mean, yes, one has to address some of these questions, that's true. But I don't know the exact answer to that question, but very likely tetrad would become degenerate at some point for the non-trivial configurations that will be relevant to such things.
Any other question? Otherwise, can I ask, you would like to comment on, you said this theory therefore violates CP.
Yes.
So that means quantum gravity theory does violate CP. I would like to ask a question to Ashtaker also. That quantum gravity theory which he has used, since it has the Imizzi parameter, it does violate CP. So what are the consequences? Has it been studied? Either you or Ashtaker, I mean, both of you can answer.
Yeah, no, I don't think we understand the consequences well enough right now. But there's certain thing clearly is that at least one parameter, which is Imizzi parameter, other ones we don't know that much, is very relevant in quantum theory of gravity. Like the theta parameter of QCD, it would have implications for standard model CP violating processes. In standard model, the theta parameter of QCD in most standard model processes comes in the combination of theta times the coupling constant of QCD. And it's this combination which is constrained by the experiments. And that combination tells us that the theta has to be extremely small, which is 10 to the minus 10 radians. Whereas the effect from the gravitation, such effects from the gravitational effects would also be multiplied by gravitational coupling constant. So normally speaking, these effects would be highly suppressed because of that, even though the counterpart of theta of QCD, which is the Imizzi parameter, eta here, is not small. In fact, it's large. But because of gravitational coupling, the effects in the standard model of physics would be suppressed. For example, W gauge boson mass would have almost no corrections because of such things. But there are some CP violating effects which are not suppressed by the coupling constants. For example, the change in the CP violating phase of the CKM CP violating phase of the standard model due to the QCD theta parameter is simply additive. It doesn't have a coupling constant suppression. But since for other reasons we believe that QCD theta is extremely small, it is irrelevant there. Similar conclusions are valid with respect to the eta parameter of gravity, that its effect in the CKM matrix, the CP violating phase of the CKM matrix would be additive. And therefore,